I wanted to work through an example that involves the magnetic force between two current carrying parallel wires. This is a famous example, an important example of magnetic forces. It demonstrates that magnetic forces are produced by electrical currents, that they are experienced by electrical currents, and it involves the field, the magnetic field, conveying, transporting, mediating that magnetic force between the two currents that are interacting with one another. So an interesting point about the force between two current carrying wires that resembles, although not exactly, the force between two charges or the force between magnetic poles, is that if you think of electrical charges, we say that like charges repel one another and unlike charges attract one another. If you think about magnetic poles, we say that like poles repel one another, unlike poles attract one another. In the case of current carrying wires, two parallel current carrying wires, actually like currents in the same direction, attract one another. And it's unlike currents, i.e. currents in opposite directions, that repel one another. In this particular problem, we're told that we've got two long, straight current carrying wires. They're parallel with one another. They're separated by 2.5 centimeters from one another. We're told that one of them is carrying a current of 1.25 amps. The other one's carrying a current of 3.50 amps, and those currents are in opposite directions. And we've got to find the force per unit length on the two wires. That means both the size of the force per unit length and the direction of that force. So let's start with the direction. I've made a sketch here of the problem. I've labeled the wire that's over here on the left-hand side. I've labeled that wire number 1. And I've labeled the wire on the right-hand side. I've labeled that wire number 2. So here's the current I1 in wire number 1. Here's the current I2 in wire number 2. These two currents are in opposite directions. So I've chosen to draw the one on the left as a current going upwards in my sketch. The one on the right is a current going downwards in my sketch. So they're opposite directions. That means that the forces between them, based on that rule that like currents attract one another, unlike currents in parallel wires repel one another, these are going to be repulsive forces. So the force on the wire on the left will be towards the left, will be pushed away from the wire on the right. The force on the wire on the right will be towards the right, it's pushed away from the wire on the left-hand side. So I'll just label these. I'm going to label them with force per unit length because it's actually force per unit length, F over L, that we're going to calculate. And they are repulsive. These two forces are opposite one another. They're equal and opposite to one another, as an example of Newton's third law. So let's calculate the size of the force per unit length on the two wires. So this is a famous equation. It was due to Ampere, who, after Oersted discovered that currents create magnetic fields, magnetic forces, as well as experience magnetic fields, magnetic forces. Ampere quantitatively explored the magnetic forces, magnetic fields between currents. And this is one of his equations, a famous equation for the force per unit length between two wires. It says that the force per unit length is mu naught over 2 pi. So that's a constant of nature that's characterizing the strength of magnetism, times the parameters of the problem, a function involving the parameters of the problem. In the numerator, there's the two currents. And in the denominator, there's the separation, I called it D, between the two wires. And this form of the equation for force per unit length is maybe not surprising in general terms. So it involves the product of the currents in the numerator. So more current in either wire means a greater force between the two wires. That makes sense. It's current that's the source of the force between the wires. So the more current, the more force. And then the force, or force per unit length, pulls off with the separation between the wires. So the further we pull the wires apart, the less their influence on one another. The closer we push them together, the more their influence on one another. That also makes some sense in terms of that magnetic field reaching out between the two wires and conveying, carrying, mediating the magnetic force. Anyway, let's calculate the value, the size, the magnitude of this force per unit length. So mu naught over 2 pi. Mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps. So if I divide it by 2 pi, I'm just going to get 2 times 10 to the minus 7 Teslas meters over amps. So that's the constant. And then we got this product of the two currents. The two currents are 1.25 amps and 3.50 amps. And then that's divided by the separation, the perpendicular separation between the two wires. That's 2.5 centimeters. I've got to put it in SI units. It's 0.025 meters. And if we calculate this number, I've already done this, I got a value that is 3.5 times 10 to the minus 5. And the units here will be the units of force, which is newtons, divided by the units of length, which is meters. So that's newtons per meter. So for each meter of wire, the force is, this is 35 micronewtons. That's 35 micronewtons per meter force per unit length on the left-hand wire. That's 35 micronewtons per meter of force per unit length on the right-hand wire. And so that's the answer to our question. Anyway, that was a simple illustration of an important law that was key in understanding magnetism. It's the force law between two parallel current-carrying wires. The force law displays an important fact that opposite currents repel one another, whereas like currents attract one another. And also it displays the fact that the force falls off not as the square of the distance, like the force between 2-point charges, but rather as the inverse of the distance, which is the case for the force between two current-carrying wires.